All right, are you ready for your joke of the day? Did you hear about the two people that stole a calendar? They each got 6 months. So today we are talking curve sketching, which isn't exactly something completely new. It is really a culmination of combining everything that we have learned about how we can get information from F. So we will still look at information about our original function that we learned in Algebra 2 and in Pre-Calc, so we can find x-intercepts, we can find any horizontal, vertical, slant asymptotes, holes with the domain, which is the domain. If you've got something radical, you might look at the domain for that as well. We know underneath the radical that it has to be greater than or equal to 0. We want to look at Y-intercepts, our end behavior, if we can know that. Usually polynomial is what we are going to know the end behavior of. So the first 4 things are all Algebra 2, Pre-Calc does not require calculus. But then we've got relative mins and maxes and increasing, decreasing that we did last Friday using F prime. And then we can go on to F double prime to figure out where we have points of inflection and where our concavity is going to change. So the whole gist of curve sketching is combining everything that you can find about F to sketch a curve that is the most accurate that we can without a calculator. So before calculus, we could get to this point, but we couldn't really know where mins and maxes were. We could kind of guess. We didn't really know where it was going to be increasing, decreasing, or where the concavity was going to change. So that's the new part that we're actually able to sketch accurate graphs. This is kind of tedious. It takes a while because you're checking for a lot of things. So that's why we are looking at 2 of them together in the notes. And then you have 2 that you're trying on your own. Now you can always fall back on actually graphing it on your calculator if you get really stumped. But I would try to see if we can figure out each piece of this information. And for now, I would just go through each thing. Can we find each thing? And then at the end, we're going to be putting it all together, which probably is the trickiest part, just putting it all together and making it make sense on one graph. Okay, so we're starting with number 7. This is number 7 in the textbook. Your directions will be the same for what you are doing, where it will just say to sketch the curve, but we're looking for all of these things. Okay, so starting with zeros. If we're looking for x-intercepts, that means that we're setting our function equal to 0. Again, these first 4, which I think I added domain, so the first 5 are just relating to F. So I'm not taking any derivatives just yet. When I go to find the x-intercepts here, cross multiplying, I just get that 0 equals x squared, and so I have an x-intercept at 0. Okay. I've got domain, which goes along with that asymptotes and holes for this case because it is rational. So for our domain, we know that that x squared plus 3 can't be 0. So our x squared can't be a negative 3. But something funny happens here. We get that x can't be a negative or positive. Negative square root of negative 3, which we know is imaginary. So if x can't be these 2 numbers that are both imaginary, that means that our domain is actually all real numbers because the only thing it can't be is imaginary numbers. So we've got all real numbers, or negative infinity to infinity for our domain. This also lets us know, remember if we were looking for vertical asymptotes or holes, that comes from excluded values either canceling or not canceling. So in this case, this doesn't factor, but our x squared plus 3 doesn't cancel with anything, so technically it would be a vertical asymptote, but then those vertical asymptotes would be imaginary, just like the domain is. So for our vertical asymptotes, holes, we have none, which is a little strange for a rational function, so we'll see what this looks like eventually. So that would be our vertical asymptotes holes. For horizontal asymptotes, remember you're using Bobo-Boatin eats DC. So in this case, we've got an eats DC. The exponents are the same. So we're dividing coefficients, and we get a horizontal asymptote at y equals 1. Okay. And for this case, I can't really know in behavior. We'll get there eventually where we're going to have to test values in between intervals, but I can't know in behavior. So this is all that we can get from f. So before calculus, that's all that we knew. So now we're going to go on to f prime, where we can talk about our relative mins and maxes and increasing and decreasing. So for f prime, we are using the quotient rule. We got the derivative of the top times the bottom minus the derivative of the bottom times the top all over that denominator squared. And this is what I was talking about in a Google Classroom post. I think it was last Saturday. Actually today. I posted it this morning. But anyway, time is weird. That whenever we're looking for critical values, that I'm going to simplify this, but then my critical values, since I'm setting f prime equal to 0, that my denominator won't be involved in the critical values, but my denominator is involved when I'm looking for where f prime is above or below the x-axis, because it is part of f prime. It just doesn't give me any critical values. So it might help to leave this as one fraction for just a little bit longer before we set it equal to 0, so that I have my final, this is what f prime looks like simplified. So let's see, we've got a 2x to the third plus 6x. I'm really hoping I don't mess up here because I don't have you all to help me, to yell at me if I do something silly. I've got my 2x cubed, and it looks like my 2x cubes cancel. That's nice. Okay, so this would be more of my simplified f prime of x equals this 6x over x squared plus 3 squared. So now if I'm finding critical values, I've got that 6x over, which technically if you wanted to lose the denominator at this point, that's fine, but you get 6x equal to 0. And so we've got an x that equals 0. So this is the only place that it could go from, f prime could go from positive to negative. It's the only place that could be a relative min or max on f. And so we just have the one critical value. So then we want to go ahead and look at whether this is a min or a max and decide from that where we're going to be increasing and decreasing. So we've got just the 0, this is f prime. Now we also talked about when we're looking at increasing and decreasing that I do have to consider that denominator, because if there is a vertical asymptote, then it could go from increasing to decreasing or vice versa. For f prime, it could go from being above to below or vice versa at a vertical asymptote, where, you know, you've got something like this. Maybe the asymptote is at 0, and then all of a sudden it goes from below to above, and it didn't actually cross the x-axis. There was a vertical asymptote. Okay, so but for this situation, for f prime, we did not have a vertical asymptote on the original, and we're not going to have one here, because that x squared plus 3 gives us imaginary vertical asymptotes, a plus or minus radical negative 3. So it doesn't have any vertical asymptotes here, but something to consider. Okay, so from there, we just need to test something negative for f prime, again, coming to the original f prime, the simplified, but not the one where we've gotten rid of the denominator. So if I plugged in something negative, my numerator would be negative, and my denominator would be positive, because anything squared would be positive. So I get a negative over a positive is negative. If I plug in anything positive, I will get positive in the numerator and positive in the denominator. So if I am going, my f prime is going from negative to positive, then sometimes it helps to go ahead and write what is happening on f. That f is going to be going from decreasing. So you could draw yourself like a line that's going down, or you could say like decreasing, increasing. Sometimes that helps to go ahead and relate right next to each other like that. And if we're going from decreasing to increasing, oh boys, I think, oh, no, I'm good. Never mind. I looked at it beforehand. I thought it had a max, but it doesn't. That's good. So since it goes from decreasing to increasing, we know that there is a relative min. So relative min at 0. And because we're going to be graphing this, we do want the y value as well. So I would be coming back up to my original, because I'm not plotting any points of f prime or f double prime. They're just giving me information. I'm looking at my original to see if I plugged in 0, I would get 0 over 3. So I'm going to have a min at 0, 0. Okay. If we're giving reasons there, we've got a relative min because f prime goes from negative to positive. Remember, that is the slopes of f. The slope of f goes from decreasing to increasing, or negative to positive. Okay, so that's what we can get from f prime. We got our increasing and decreasing. We've got our relative extrema. So the last thing, I told you it's a marathon. The last thing is looking at f double prime. And this is where it also was helpful for us to simplify our f prime, because I want to use that to find my f double prime. It's also where it is really important that I'm being careful with finding my derivatives, because if my derivative is wrong, then everything that I am getting from it is going to be wrong. Okay, so for f double prime, again using the quotient rule, we've got the derivative of 6x times this x squared plus 3 squared. I'm sorry, I'm kind of crooked. Minus the derivative of my denominator. I do have to use the chain rule for, so we've got a 2x squared plus 3 times the derivative of the inside, so 2x, and then times the numerator, 6x. So saying that again, this whole 2x squared plus 3 times 2x is the derivative of my denominator here. So derivative of that. So using the chain rule, bringing that 2 out front, x squared plus 3, and then times the derivative of the inside is 2x. But then using the quotient rule, I'm still multiplying by the numerator at the end. Okay, then we've got our denominator squared, so that x squared plus 3 is now going to be raised to the 4th. Okay, so similar to our f prime, I'm going to keep this guy for now because it is going to be important when I'm deciding positive or negative, but I want to simplify my numerator. So we've got, what do we notice? And really, anytime you have trouble distributing, like I was about to distribute and then realized that that was squared and was like, oh, I don't really want to do that. We are noticing that we've got an x squared in both of these. Happens anytime I've got product rule or quotient rule and there's a chain rule, because this guy is just that with one more power. So I can take out an x squared plus 3. I can also take out a 6. This guy has a 6 and this has a 6. So I'm going to go ahead and take out a 6, x squared plus 3. And again, the reason that we're not multiplying this out and instead I'm factoring it is the reason we're going to use the numerator is to find those points of inflection. I'm going to be setting this equal to 0 and then solving, and that will involve the numerator. I will want it in factored form anyway, so that's why I'm doing that. So we're taking out the 6x squared plus 3, which means we're left with an x squared plus 3 on the left of the negative. I don't really need it in parentheses. And then over here, we've got a negative 2, the 2x, and that's it. Oh, and this x. So I took out an x squared plus 3, and then I took out that 6. So I'm left with a negative 2, a 2x, and an x. So negative 4x squared. One more simplify here. And we've got, you guys may have done it all in one step. You're so smart. to the 4th. And it looks like once we have it in factored form, we can actually cancel one of these x squared plus 3's. So there's a hole there. That's not going to hurt anything. If you want to cancel that here, you can. We've got a 6. So one of these guys, and then that would take it down a power. Since it's all multiplication, I'm allowed to do that. So we've got a 6, negative 3x squared plus 3. And then now an x squared plus 3 cubed. And I'm going to need another piece of paper. So I finally have my f double prime. I am setting that equal to 0 so that I can find my points of inflection. Plus 3 to the 3rd. Woo. And then my denominator does go away. I will have to consider it later when I'm looking at positive or negative, but as far as my point of inflection is concerned, I am just looking at the numerator. I can also divide both sides by 6, so then I'm just looking at this negative 3x squared plus 3. I can subtract my 3 over. Divide by negative 3, so just have a 1. And we find that x is positive and a negative 1. So I've got, it looks like 2 points of inflection, but remember, just because f double prime equals 0 doesn't mean it has to be a point of inflection. It does have to change signs. Doesn't matter how, but it's got to change signs from positive to negative or negative to positive on f double prime to be a point of inflection. So we've got a negative 1, a positive 1, and I'm going back to my simplified f double prime up here to test values. I'm going to start with 0 because it's just easy. Plugging in 0, I get a 6 times 3 and a 3 cubed in the denominator, so those are both positive. If I plug in a negative 2, let's see, this will be positive, so overall, oh well, I better actually try something. Negative 2 would make this a negative 12. So overall, the numerator would be negative, the denominator will be positive. If I plug in something positive, positive 2, I have the same situation because they're both squared. So if I plug in 2 here, I'll still get a negative 12. The numerator is negative, the denominator is positive, which we expect for this to alternate, but sometimes it doesn't. So we always want to test values. Okay, so this lets me know that I do have points of inflection at x equals negative 1 and x equals 1. Again, because we are actually sketching this whole curve, I do want to go ahead and plug in both of those values to see where that's exactly happening. So we've got a negative 1. If I plug that into my original, I've got a 1 over 4, so 1/4. So back into this guy, plugging in the negative 1, we get a 1 over 4, and that's going to happen for 1 as well. So 1/1/4 is my other point of inflection. We can also see from our f double prime where it's negative, positive, and negative, and we know this because we've got those points of inflection, so that concavity has to be changing, but at that negative infinity to negative 1, this is where we're concave down, and then f is going to be concave up and then concave down. So that's what we have found out there. Okay, so that was a lot of information. Now we are putting together everything that we know. So starting back from the beginning, that we had an x-intercept at 0. Not only is it an x-intercept, but it ends up being a relative min, so that's important. We also had let's see, our domain is all real numbers. We've got a horizontal asymptote at 1, so I'm going to make, that's going to be my 1. Okay, so we also know that this is our relative min. We know, oh, I think I made this really short. That's okay, I'll make a bigger one a bit later. We've got, that is our relative min. It's going from decreasing to increasing at that place. But we also found that we have points of inflection at 1 1/4, and at -1, 1/4. So we're at 1, 1/4, -1, 1/4. Those are our points of inflection. And we're wanting to make it concave down to now concave up in between here, and then concave up still to concave down. Okay, so this is what we're looking at. If we are connecting these and using our concavity, our horizontal asymptote here, this function is going to look something like this. Where notice our concavity changes. At that point of inflection, it was concave down, all my tangent lines will be above it, to now concave up in between, and now we're concave down. We want to make sure our increasing and decreasing makes sense, that we are decreasing and then increasing after 0. And that is what our curve looks like. I'm not sure why I made the horizontal asymptote so low. I should have given us some more space for this, but that is what number 7 looks like. Okay, the other one that we're going to look at is not going to take as long because I'm not going to explain myself as much. So we're just going to jump right in to looking at zeros. Setting our h of x equal to 0. Oh, we never found a y-intercept on that last one, did we? I think I skipped right over it. It ended up being at 0, 0, just like the x-intercept, but anyhow. So setting both of our factors equal to 0, we can square both sides. We get zeros at positive or -2. I'm looking at the domain for this problem. I am going to have an issue with the denominator that I want that x minus, or sorry, not denominator, underneath the radical, 4 minus x squared has to be greater than or equal to 0, which the easiest way to look at something like this is to look at the graph of that. So we know the x-intercepts, it was this. X is going to equal a -2 and a +2. And then looking at where that is greater than 0, it is a parabola that's facing down. So that means it's going to be negative, negative. So the only place where it is going to be greater than or equal to 0 is from -2 to 2. So that's a little strange for this one, that we've got this domain from -2 to 2. We won't have graph outside of that. Now, for asymptotes, holes, we don't have a rational, so we won't have asymptotes or holes. I can find y-intercepts. Remember, for a y-intercept, that just means that x is 0. So my h, or my y value, is going to be this 0, 4 minus 0 squared. So we do have a y-intercept at y equals 4. And that is all that we can get from h. So now we'll go on to h prime. We do want to use the product rule. So we've got the derivative of x times the square root of 4 minus x squared plus the derivative of square root of 4 minus x squared. Be careful here, we've got a 1/2, 4 minus x squared to the -1/2, and then multiplied by the derivative of the inside using that chain rule, -2x times the first. Okay. So we'll want this to be one fraction before we can compare things. I can cancel my 2's, but that's it. So we've got a -x squared still in the numerator. In the denominator, we have that square root of 4 minus x squared. And then when we're combining, getting a common denominator, I need to multiply this by the square root of 4 minus x squared, which which means that is now just 4 minus x squared, and then we have minus x squared, so a 4 minus 2x squared. So this is my h prime. Okay. So using this for critical values, I would look at my numerator of h prime equaling 0. So we get a plus or minus radical 2. Okay. And then we are looking at that on a number line so that we can see whether they are relative mins or maxes. We want to consider the original function using that denominator to know where it changes. Again, we would want to look at this denominator to know if we have other places that it changes, but for this denominator, if we set that equal to 0 to look for vertical asymptotes, we're going to get the same thing that we got for our domain. So that -2 and 2 is where it could change signs, but that's where our domain ends. So it's not really going to affect us because that's the end of the domain. Technically, if it was an all real number situation, then we would want to include those vertical asymptotes at -2 and 2, but they're actually not vertical asymptotes. It's where it's going to end. Okay. So plugging in 0 to start with, so that's 0 and that's 0, we get a positive number on top and bottom. If we plug in a -1, we do want to plug in something on the domain because otherwise we'll get undefined down here, or an imaginary number probably. Negative number on -1 here would give us positive overall, a 4 minus 2, and a -1 here would give us yeah, it's positive as well. Are we staying positive? What happens if we plug in a positive 1? We got 4 minus 2 and 4 minus, so do we stay positive this whole time? Dun, 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 dun. No, it should be negative here. We're decreasing. Did I do something silly? -1 squared 4 minus 2. Plus for a second. Wait. No, I'm just a goober. Negative radical 2 is not less than -1. So -1 is still in this interval. That's why I was getting positive. So we could plug in -2. It is our endpoint, but that will let us know what's happening over there. Plugging in -2, I am going to get, well, do I get 0 here? Yeah, so I can't even plug in -2. Let's plug in -3/2. Is that going to be disgusting? We should get negative out of it, but let's see. -3/2 would be 9/4 times 2. Oh goodness, my brain, it's too early in the morning. 9/2, but it would be a -9/2, which is 4.5. Okay, so good. We get a 4 minus our 4.5, so that would be negative. Goodness gracious. And then here, if we were plugging in 3/2, you get that 4 minus 9/4 would be, or not 9/4, 9/2. No, 9/4. Oh goodness, guys. It ends up being negative. Are you like yelling at me right now? It ends up being negative. Goodness gracious. We have to move on. If I'm plugging in a positive 3/2, it is also going to end up being negative. Because I've got those x squared, so these are both going to have the same sign. So it ends up being negative. So this is my h prime. So that means that h at negative radical 2 and radical 2, we're going from decreasing to increasing to decreasing. So we've got relative mins and maxes happening. At negative radical 2, because it goes from negative to h prime goes from negative to positive, and h goes from decreasing to increasing. We've got a relative min. I'm going to find the y value, and then because we're going from, h prime is going from positive to negative, or h is going from increasing to decreasing, we've got a relative max at radical 2 something. So then I'm coming back to my original to plug in my negative radical 2 and my positive radical 2. We've got negative radical 2 times, let's see, 4 minus, if we're plugging in a negative radical 2, we would end up with a positive 2 there. Times radical 2, so a negative 2. That worked out kind of nice. And so our negative radical 2, negative 2. And then I believe something very similar is going to happen if we plugged in a radical 2 instead. This part is going to be the same. The only thing that's different is the sign in the front. So instead of getting a negative 2, we'll get a positive 2. So that's my relative mins and maxes, and I've got my increasing, decreasing going on as well. So moving on to h double prime in our points of inflection. So using our h prime of x, we are using the quotient rule. We've got the derivative of the top is a negative 4x times the denominator is a 4 minus x squared minus the derivative of the denominator is going to be a 1/2 radical 4 minus x squared. And by the way, one of them that I gave you today is a polynomial, so you're welcome. A negative 1/2, and then multiplied by the derivative of the inside, and then times the numerator, oh, I ran out of room, 4 minus 2x squared. 4 minus 2x squared. Can we pretend that we know what that says? All over, this is kind of nice, our square root of 4 minus x squared squared, which is just going to be 4 minus x squared. So after all of that nonsense, and then this ends up just being 4 minus x squared, it almost feels not even fair there. Okay, so our h double prime, you gotta clean this sucker up. The ultimate denominator is fine, but this guy's pretty gross. So we do have parts that are in the numerator's numerator, and then we've got our 2's cancel again, so that's nice. And then that's about it. We're left with a negative x in the numerator, so negative negative x we can go ahead and add, and then we have this 4 minus x squared, 2x squared, yeah, 4 minus 2x squared. And then this part can go in the denominator, or 4 minus x squared. Okay, so we're almost there. Now we need our common denominator with the numerator part. So multiplying this by a square root of 4 minus x squared will just get us a 4 minus x squared there. I'm going to go ahead and distribute my negative 4x to, well, I don't know that we're going to want to do that. No, we'll want to factor from there because we've got a 4 minus, that's 2x squared though. And this is, oh, we're not going to be able to do that. Okay, we will need to. So just noticing that I can't factor, once this is a 4 minus x squared, this is a 4 minus 2x squared, so I won't be able to factor that whole thing out. So that tells me I need to go ahead and distribute my negative 4x. Okay, so we're getting a common denominator for the numerator part. So whenever I multiply this by the square root of 4 minus x squared over the square root of 4 minus x squared, this becomes 4 minus x squared. I want to distribute that negative 4x to both, so we have a negative 16x plus 4x cubed, plus I'm going to distribute here to 4x minus 2x cubed, all over our square root of 4 minus x squared. Okay, so now I'm going to take one more And we are going to simplify here. So I've got a 2x cubed and a negative 12x. So that's not too shabby. And then if we multiply by the reciprocal, so if I multiplied this whole thing by 1 over 4 minus x squared, these are the same. So since one of them is a square root and one of them is not, I would be adding the powers to multiply. So 1/2 and 1 would make this 4 minus x squared to the 3/2. Which in the end, figuring out my points of inflection, I'm just setting that numerator equal to 0 anyway. I went ahead and made my graph down here. It was all ready to go, and now I'm running into it. So I've got, factoring out a 2x, we have an x squared minus 6. So we end up with 0, and then a square root of x and a negative square root of x. Square root of 6. I don't know why I'm saying x. But remember, our interval is only from -2 to 2. So the square root of 6 would be greater than the square root of 4. So these guys actually will not be involved in our graph. So we're only looking at x equals 0 for f double prime, or h double prime, whatever letter we are using currently. And then looking at my original, this is why I needed that denominator. It seemed like it was not worth it, but we do need it for this part, that we can plug in something to the left of 0, so a -1 would be -2 times a positive 12, so that would be positive, and then a -1 here squared, that would be positive. So a positive over a positive, positive. So that means that it's concave up. Yeah, it's concave up to the left of 0. If I plug in a positive number, plug in 1, I'd have a 2 minus 12 is negative, and then positive in the denominator, so we'd be negative to the right. So for just h, it is going to go from being concave up to concave down. So we do have a point of inflection at 0 something, plugging into our original function, our 0, we would get 0 times something, which is 0. So our point of inflection is at 0, 0. Whew. All right, we are finally ready to put it all together. So for our graph, we did not have any asymptotes or holes. We had zeros at 0, and then also at a plus or minus 2. And that is also the domain, so that means I won't have anything on either side of those things. I have a relative min at negative radical 2, -2. So now I know that is slightly to the left of -1. I don't know what I was thinking. Here, negative radical 2, -2, so about right here. And then we've got a radical 2, positive 2. So radical 2, positive 2. And for those, on the last one that we were looking at, it was at 0, 0, so it wasn't really necessary to label, but I would go ahead and label those. We can see where the x-intercepts are at. And then using our concavity, this is making some sense because it should be concave up to the left of 0, so we're looking at this, and then it's concave down to the right of 0. So connecting what I know, we've got, and remember our point of inflection is just at 0, so it's going to stay concave up until we get to 0, and now it's concave down. So it ends up looking like this. So for all that information, it doesn't look super crazy. I do want to double check my increasing and decreasing, that I had it decreasing from -2 to negative radical 2, and then also from radical 2 to 2. And then I have it, yes, it was decreasing on either end, sorry. It was decreasing on either end, and then in between from -2 to 2, I was just looking at this. And from -2, radical 2 to radical 2, it should be increasing, and it is. Whew.